So just a little recap before we get to the next page. The first part of the fundamental theorem of calculus says that the derivative of the integral of f is just the function f itself, because integration and differentiation are inverse operators. They do and undo each other. Part 2 of the fundamental theorem of calculus says that the definite integral of some function f is given by evaluating its antiderivative at the upper and lower endpoints. And again, the integral undoes the derivative. Okay, now let's take a look at some more examples of using the fundamental theorem of calculus, part 2. And so we have some more functions here that I can do. Again, we want to find the antiderivative and evaluate them at lower bounds and upper bounds. So first of all, we've got our 60x. When I take the antiderivative, that's going to be 60x squared divided by 2 minus 6x to the third divided by 3. So we're adding 1 to the power and dividing by the new power. And again, adding 1 to the power, dividing by the new power. That's the antiderivative. And now we're going to put on a boundary. So we're going to go from 0 to 10. Okay. Now, when I evaluate this, if I forget to talk about c, I'm going to write a c over here just to remind myself to talk about c. Where did c go? Because when we did the antiderivative, we had a plus c on that. Why am I not using it? I'll talk about that in a second. So the next thing to do, though, is to plug in those upper bounds minus those lower bounds. Or actually just get that reduced, because I have divided by 2's everywhere when you could reduce that. So we're going to have 30x squared minus 2x cubed evaluated between 0 and 10. And so now we'll start plugging things in. So we've got our 30 times upper bound 10 squared minus 2 times upper bound 10 cubed minus 30 times 0 minus 2 times 0. And not all the time do those cancel out to 0. The lower bound isn't even always 0. It's just when they happen to be 0, that went away. And so I just have the, this is going to be 100 times 30, so that's 3,000 minus 2,000. And so the answer to the integral is 1,000. Okay, so that's the answer to this definite integral. So indefinite integrals, we get a function, and definite integrals, we get a number for the answer. Now, back to this c for a second. So if we took the antiderivative of this function, it wasn't bounded, we would have had a plus c on the end there. The reason that I don't need plus c, it's an arbitrary constant, is that I would have that arbitrary constant here, and I would be subtracting it back off here once the negative distributed. So that arbitrary constant would cancel, and so for the definite integrals, we don't include it, because we're just going to cancel them back off. What's the point of writing extra characters down? So it is still there. It absolutely is there in the definite integrals. We just don't need it because they are always going to cancel off. Because c is not cx, it's just c. They're going to reduce with each other. They're not going to be 0 over here. They're going to actually cancel. So that's why we don't write c for the definite integrals. We certainly need it in the indefinite integrals because there's nothing to cancel with. There's no subtraction that's bounded like that. Okay, so that's what happened to c. All right. Looking at the next part, again, we want to do an antiderivative. We cannot do one in this format, so we're going to rewrite the original. And so we could distribute that denominator. So we're integrating between 1/16 and 1/4 of, okay, so that is t to the 1/2 power divided by t. So that first piece is t to the negative 1/2 power. And then minus 1 over t. I could write that as t to the negative 1, but I don't want to, because t to the negative 1 is not a power function. Instead, it's going to integrate into the natural log. So we'll use the power rule on the negative 1/2 power. So if I add 1 to that, it's going to be t to the positive 1/2 power divided by 1/2, which is multiplied by 2, minus the natural log of the absolute value of t, bounded. Instead of plus c, we're just going to bound it between the lower bound 1/16 and the upper bound 1/4. Okay. Remembering that 1 over t does not use the power rule. You can't use a negative 1, add 1 to it and get 0 and divide by 0. Instead, that integrates into the natural log. Okay. Now, when I plug in upper bound minus lower bound, for upper bound, we have our 2 times 1/4 to the 1/2 minus the natural log of 1/4. I can drop the absolute value as soon as I know I'm plugging in a positive, minus the quantity 2 times 1/16 to the 1/2 minus the natural log of 1/16. Okay, so that's not 0 for sure, so we definitely want to make sure we simplify each of these. I know that 1/4 to the 1/2 power, that's the square root. It's a half because the square root of 1 is 1, the square root of 4 is 2. So that's 2 times 1/2 minus, okay, just to get this simplified, let's rewrite this as the natural log of 1 plus the natural log of 4, because we're going to be able to get rid of the natural log of 1. Lots of different ways to simplify this, but what I'm actually doing is separating this into minus the natural log of 1 minus the natural log of 4 with that quotient rule, and I just distribute that negative. That's why my natural log of 4 is positive, because of this negative. So quotient property there. And then the advantage of this is that the natural log of 1 is 0, so we're going to be able to simplify this down to just the natural log of 4. And we'll simplify it a little further in a little bit here. Now if I distribute this negative, I have minus, okay, so this is 2 times 1/4, because the square root of 16 is 4. That's going to be plus, and then I have the natural log of 1 minus the natural log of 16. And again, the natural log of 1 is 0. Okay, so just keep simplifying this to get our final answer in exact but simplified form. We've got 1 minus 1/2, just looking at the two fraction values here, plus, now if you have two natural logs, you can definitely simplify them, so let's get them combined. Because 16 and 4 are both powers of 2, that's probably the best way to rewrite them. So if I have natural log of 2 squared minus natural log of 2 to the 4th, we can use the power property to pull the coefficients down, and then we'll be able to combine those as well. So I'm going to have negative 1/2. Okay, so 2 natural log of 2 minus 4 natural log of 2 is going to be negative 2 natural log of 2. And that's going to be the simplified answer. Okay. Now, before I forget to mention this, we can also integrate these lovely things on Desmos. So let me go up, get a new graph. So I can integrate. You spell integrate I-N-T. When you hit the T, boom, you're ready to do a definite integral. So I can type in my lower bound of 1/16 and my upper bound of 1/4. Then our function, which is the square root of, I'm going to use the variable x just because it makes it easier to type, minus 1 over x dx. And I have that lovely number, which if I type in my answer of negative 1/2 minus 2 natural log of 2, I do not have the same thing. So I actually figured out what I did. I actually have an extra negative right here. This is positive, of course, because 1 minus 1/2 is positive 1/2. So my mistake in keeping the negative an accident there. So if I go back over there, Desmos lovely was able to help me check my answer. Now that I have it typed incorrectly with the positive 1/2, they do match. So I can type in these indefinite integrals. I can do the same thing to check the one on the top of the page. INT integral, this one was from 0 to 10 of the quantity 60x minus 6x squared dx, and we get 1,000, and 1,000 is what we had up there as well, so that's perfect.